This video is a recap of the development of the theory of plate tectonics. Okay, so first we know that plate tectonics theory was started by Alfred Wegener, and Alfred Wegener proposed a theory called Continental drift theory, in which he said that in the past there was this Pangea, which is a supercontinent, and then that supercontinent broke down into the individual land masses that we have now, and those land masses moved through unmoving oceans. Okay, and again, from the perspective of Alfred Wegener, this is very obvious because back during that day, during that time, people already noticed that the shapes of the continents fit together like a jigsaw, right? So a lot of scientists actually already noticed that. But what is different with Wegener is he actually went out into the world, flew into these continents, and kind of investigated if if the shape was it just a coincidence or there's really reasonable there is really an evidence to point out that the shapes are really edges that were once connected together, right? So make no mistake, other people already noticed the shape of the continents, but Alfred Wegener gathered evidence for that theory to be proposed. Now, the only problem was Alfred Wegener again had no idea of why the land masses would move, and because he was only exploring the continents, he wasn't able to really see what is happening on the sea floor. Okay, so remember during his time there were no submarines, no imaging devices that could map the ocean floor. So obviously he was limited. He could only explore the continents, and so he proposed that maybe the continents moved or drifted over the unmoving ocean or seafloor. So he thought that the seafloor was static, and it's the continental land masses that are moving through the surface of the seafloor. Okay? Now, again, he proposed a lot of evidence. The problem was he could not provide the reason or the force or why the continents would move in the first place. He just took note that from the evidence, it seems to point out that these continents drifted apart from once a supercontinent called Pangea. Okay, that was a start. Then after that, Harry Hess and Robert Dietz came into the story, and you have to remember this is after World War II, and in World War II, nations started to develop submarines, and submarines were able to map the ocean floor, and so they saw what Wegener wasn't able to see, and what they saw was that in the middle of the ocean, sometimes you see these cracks, right? And then these cracks would spew out magma materials from underneath the earth, right? And obviously you see deposits on the sides, and now we call this an oceanic ridge, right? But they saw that magma comes out from the crack in the middle of the ocean, and so they observed more, and they concluded that when magma comes out here, this piece of the ocean floor gets pushed towards the side, and this also gets pushed towards the side, and therefore moving the seafloor or spreading the seafloor, so to speak. So that's why they call their theory the seafloor spreading theory. So in their concept, they thought that hot magma rises from the mantle and creates a crack in the Earth's crust, which we call an ocean ridge. The magma pushes the two sides of the seafloor, causing each to move sideward, spreading the seafloors. And this magma fills in the gap, the crack, and solidifies and forms new seafloor. Okay? So, they thought that there is this process that is creating the new seafloor. So, like this. So, magma comes out, the seafloor gets pushed to the sides, and what do you if you look at the seafloor, it's connected to the continents, the continental crust. So therefore, when the seafloor moves, the continents also are pushed by the same force, and they also move. And so therefore, the question that Wegener was not able to answer was answered by the seafloor spreading theory by Harry Hess and Robert Diaz. Namely, the continents drift because the oceanic floor is connected to the continents. Remember, oceanic floor is basalt and granite, basalt, but while continental crust is basalt plus granite. So you can think of it as the continental crust is really built on top of the oceanic crust. So why would the continents drift? Because the oceanic floor spreads in sites called oceanic ridges. And why would the oceanic ridge move? Because magma comes out from it, and this is from observation. They saw boiling oceanic water. When magma comes out, they see newly formed seafloor from the molten materials that are coming from the inside of the earth, and therefore that was the theory that they proposed. Okay, now again, as in the same manner as in all of sciences, when we get an answer to a question, sometimes we get another question, and or most of the time we get another question. So the thing is, okay, now we know that there's this oceanic ridge and the seafloor spreads, moving the continents with it. But why would magma push, or why would magma create a crack and rise out of that crack in the Earth's crust? Okay, so it's a question. So here your question was, why would the continents move? Then you answered it through the seafloor spreading theory. But then that seafloor spreading theory proposes that magma comes out from the ocean floor. And obviously that's an observational fact. They saw that magma really comes out from the oceanic ridge. But why? Why would magma rise up from the oceanic ridge? Okay. So at this point, scientists are starting to know the structure of the Earth, and obviously they have been studying heat in the past century or so. And if you remember your discussion in grade 7, heat transfer comes in 3 flavors. You could have conduction, convection, and radiation. So to answer this, scientists argue that in the Earth, we have a layer called the asthenosphere. And this asthenosphere is again fluid-like. And if this asthenosphere is fluid-like, then it should be just like in any, just like a situation where you have a fluid inside a container, right? So namely, for example, this one, if you have a fluid of water, and then you heat it on top of, you put it on top of the stove, you light the stove up, so there's fire here. So the stove kind of heats the material here. And again, when the materials are heated, they expand, their density becomes less, so therefore they float up. And then as they are farther away from the heat, they cool down because they're not far away from the heat source. And then they sink back down, but obviously they can't sink down on the same path because there are materials that are rising here. So they sink down on the sides, and therefore creating this currents, this cells of circulating fluid. Okay, so scientists now argue that, hey, if that happens in a pot of water with a heat stove, with a stove as a heat source, that could very well be happening in the Earth. It could be that the core of the Earth, the center of the Earth, is heating this asthenospheric layer, and because of that, there are currents that are created because the heated part rises up, and then the parts that are far away from the heat source now cools down, and obviously when they cool down, they have to sink back down, but onto the sides, creating these convection currents. And scientists are arguing that maybe the upwards motion of the current is what is pushing the magma to come out of the cracks, or another way to say it is maybe the upwelling of magma here creates the cracks, and that's why magma comes out from the crack or asthenospheric materials, right? So if you notice here, this is really an evolution because you started with the the observation that continents drift, right? You don't know why. And then you realize that there's something wonderful happening in the seafloor, namely in oceanic ridges, where magma comes out, and therefore you piece this narrative that maybe it's the magma that pushes the seafloor to move, and the seafloor is connected to the oceans, out to the continents, and therefore the continents drift. But then again, you have a question: why would magma come out? Then you turn to a thermodynamic or a concept from thermodynamics, which is convection currents, because after all, we know that the asthenosphere is fluid-like. So if it's fluid-like, just like any fluid subjected to heat, it should form these convection currents. And maybe the places where the convection current is going up, that creates cracks in the Earth's surface, creates ocean ridges, and therefore magma comes out from that. Okay? But then again, just like everything else in science, question is always followed with other questions. Okay, cool. There are convection currents in the stratosphere, right? But why would the Earth's interior have convection currents? Well, again, the answer is because it's like a pot of water being heated, right? So it's like a pot of water being heated because if you think about it, in this scenario, the heat source is below at the bottom, right? And if you review our internal structure of the Earth, what do we get? We have the core, right? At the center of the Earth. And if you trace the temperature, it's the inner core or the core that is the hottest, that has the hottest temperature, as high as 7,200 degrees Celsius. So therefore, just like a pot of water is sitting on top of a heat source, you can think that the core serves as the heat source, serves as the stove in this analogy, serves as the stove, and the materials from the asthenosphere is the fluid that is being heated by that stove, and therefore it's plausible to create convection currents. Okay. Now again, this is still debatable. Some scientists say that the convection currents only appear in the asthenosphere because it's the asthenosphere that is fluid-like. But some would also say, well, there's also motion in the mesosphere, although it's not fluid-like, but maybe it could be whole structures of rock moving. So it's like a fluid, but more macro scale, so to speak. But it doesn't really matter. What matters is that you have circulation of materials, and that circulation of materials feeds the magma to come out. The moving out of the magma feeds the ocean floor, makes the ocean floor move. The movement of the ocean floor causes the continents to drift. So therefore, you now have this coherent story of why we see the continents drift. That's because, of this. We first proposed that the continents drifted, not because we had any reason to believe that they, not because we know what pushes them. We did not know, but all the evidence points to the fact that they move. So Alfred Wegener proposed that, and then he did not know again what was happening. He did not know what was happening on the seafloor. When Harry Hess and Robert Dietz had submarines and they explored the ocean floor, they realized that there are ocean ridges and magma comes out from it, and therefore they kind of provided another side of the story that kind of really not disproves continental drift theory, but sort of improves upon what the continental drift theory is saying. And then after that, if we combine that with the concept of convection currents and what we know about the internal structure of the Earth, it all makes sense. It all makes sense. And these theories, okay, continental drift theory, the seafloor spreading theory, and then our concepts of convection current. Obviously, this is not credited to a specific person because this was, discovered way back before we even had any idea about plate tectonics. And then the internal structure of the Earth. Obviously, knowing the internal structure required a lot of studies, not just credited to specific persons. But in a nutshell, if you add continental drift theory and improve upon it through the seafloor spreading theory, and then add your concept of convection currents and add your concept of internal structure of the Earth, you get plate tectonics. Okay, so what we're saying is plate tectonics is kind of like the evolution, the result of the evolution that was evolution of theories that was started from Alfred Wegener's continental drift theory. Okay, so now we understand. Now we know that it's not that the ocean floor moves, but the lithosphere itself is divided into segments called plates, and it's still the same case where magma comes out, pushes the plates, so therefore the plate has this movement, and these movements could be diverging. When this diverges, obviously this has to hit something on the other side, so there might be convergence here, or there might be sliding, so there might be transform. So now we have the boundaries. Once you have the boundaries, you could say that when you have convergence, one would subduct under the other, forming a trench. This melts, forms volcanoes here. If it's oceanic, it might form volcanic islands, and so on and so forth. So therefore, from there, you can explain almost anything, any structure that you find on the Earth. Okay? So you're wondering about how come volcanoes happen? It's because of the convergence of plates. How come mountains are there? It's because conversion of two continental plates. How come there's a trench beside the Philippines? Because of the conversion of plates. How come there are underwater cracks in the middle of the Atlantic Ocean? It's because of divergent plates. How come how come in California there are strong earthquakes? Well, because there's a transform plate boundary there called the San Andreas Fault. So all of these features. So you can even add in like a tsunami. Why would tsunami happen? Because of the earthquake, it displaces the ocean water and therefore creates the tsunami. So therefore, if you think about it, once you have that theory, you can now explain the features, how geological features are built. Okay, so the theory that you can come up by that would give you a tool to explain how mountains come about, how trenches come about, how earthquakes come about, and how volcanic islands come about, and all of those geological features. So therefore, it's really the building of the Earth's surface, right? And that is how this word was chosen. Obviously, plate tectonics, because the players there are plates or segments of the lithosphere. But more importantly, why do we choose the word tectonics? It comes from the word tecton, and tecton in the ancient world is related to carpentry, right? But more than that, more than carpentry, it's really the sense of building something from scratch, right? Like, for example, if you have a piece of wood, you could do carpentry and make a stool from that wood. So it's really the sense of building something from something more basic. So if you think about it, we are building all of these geological features of the Earth because of the interaction of plates. So that's why we use the word tecton. So again, let me clarify. Tecton is really literally it would be translated as carpentry, but it's not the carpentry itself that's the reason why we chose the word tecton, but it's the sense of the sense that carpentry evokes this this idea of building something or making something or transforming some basic material like wood into something more complicated like tables and stool. So the same manner, the basic interaction of plates actually builds all of these geological features that we see now on the Earth. That's why we call it plate tectonics. But again, it is a labor of love of many different scientists contributing. So it's not really like the theory of general relativity, wherein there's only one scientist who thought of that, like Albert Einstein. But in the case of plate tectonics theory, it's really a lot of scientists and a lot of concepts that are pulled together that evolved into what is plate tectonics now. Therefore, we don't credit it to anyone. We can say that Alfred Wegener kind of pioneered the field, yes, but if you say who proposed plate tectonics theory, you could not answer the question because it's an evolution of the theories before it. And again, the theories before it were primarily first the plate tectonic theory, followed by seafloor spreading theory, plate tectonic theory by Alfred Wegener, seafloor spreading theory by Harry Hess and Robert Dietz, and then the concept of convection currents, which we don't really credit to any specific person because we already know this beforehand when we studied heat. I mean, this was already known even before plate tectonics came about. And then internal structure of the Earth. Obviously, this was not just discovered by just one person, but it's a conglomeration. It's accumulation of knowledge from different studies of the Earth. So therefore, that's how your plate tectonics developed. It came from theories that evolved and evolved and evolved, and you add many different concepts until it became the plate tectonics that we know